Hello. So we reach here lecture 16, and we are in chapter 5, that is thermal properties of solids. So what did we discuss last time? We discussed last time um, about the heat capacity in different models. Okay, so we said that for a very long time, it was understood that the heat capacity is equal to 3 kb, and that is introduced by DeLong and Petit. Actually, this is known as the law of DeLong and Petit, that the heat capacity is equal to 3 kb, where kb is the Boltzmann constant. This formula is okay for most metals, for most solids, okay? But it did not explain what was happening at low temperatures. So this was okay at room temperature. However, for very low temperatures, this formula was deviating from experimental data. So Einstein came in 1907 and he introduced quantum mechanical ideas in order to solve the problem at low temperatures. And although he could really account for the formulas, but again, as a result, what he obtained was only okay at room temperature. So still he could not explain what is happening at low temperatures, especially that it was found that the heat capacity at low temperatures was proportional to T cubed. So what are we going to do today is to solve one problem using the classical method, that is using what DeLong and Petit did, and we will obtain that C will be 3 kb, exactly what they obtained. And then we are going to solve another problem using Einstein's model and find the result that Einstein obtained, and we will be sketching together how the heat capacity as a function of kBT will look like. So let's start. So more or less today's session is a problem solving session. So we will start with the problem 1, the law of DeLong and Petit. Okay, so this is according to the law of DeLong and Petit. So the Maxwell-Boltzmann distribution is the classical distribution function for distribution of an amount of energy between identical but distinguishable particles. Mathematically, the Boltzmann distribution can be written in the form of f of e is equal a e to the minus beta e. What does it mean, the Boltzmann distribution? This is the probability, okay? So this is the probability that a particle would have an energy E. So the probability that a particle would have an energy E is given by f of E, which is a e to the minus beta e, and it's given what is beta, it's 1 over kBt. Now, we need to show that the distribution function for one-dimensional kinetic energy is given by f of Vz is equal beta m over 2 pi to the half e to the minus beta half mvc squared, and they're giving me a hint to do this integral value. And then we are going to use this distribution function to find what is the expectation value of Vz squared, okay? And then when we find Vz squared, we're gonna find the average kinetic energy, because kinetic energy is nothing but half mvz squared. And then we have to show that the average kinetic energy in the 3-dimensional is equal to 3 over 2 kBt, which should result in heat capacity C should equal to be 3 kBt, which is the law of DeLong and Petit. So let's do one step at a time. So we will start with showing that f of Vz is equal to this thing. Okay, so the solution. So we know that here I put in the corner that f of E is equal a to the minus beta e, and we need to show that f of Vz is equal to this constant multiplied by e to the minus beta half mvz squared. We are going to use this hint. So the first piece of information where we will start from, so this thing we will call it A. So we have f of Vz is equal a e to the minus beta half mvz squared. And we need to find what is this A, okay? So we will start with the idea that if this is the probability to have a value of E, then the integral from minus infinity to infinity of this thing dvz is equal to 1, which means the summation over all probabilities should be equal to 1. So the integral of a e to the minus beta half and vz square is equal to 1. The a is just a constant, it goes outside, of the integral of this thing is equal to 1. Now let's take that b mvz square over 2 to be equal to x. Okay, this will facilitate my life. So if I take this to be equal to x, then if I take its, then vz will be the square root of 2 over beta m times x. And if I take the dvz will be the square root of 2 over beta m dx. And now I know that a multiplied by the integral from minus infinity to infinity, dvz is nothing but square root of 2 beta m dx, okay, multiplied by e to the minus x squared, and this is equal to 1. Now, this thing here is also a constant, so it also goes outside the integral. So I will have a square root of 2 over beta m, integral from minus infinity to infinity of e to the minus x squared dx is equal to 1. But the integral of e to the minus x squared dx is equal to, I'm going to use this thing over here, the integral of e to the minus au squared du is square root of pi over a. Here I have a is equal to 1 because it's just minus x squared. So the a is equal to 1. So the integral of this will be square root of pi, implies a square root of 2 beta m, 2 over beta m times square root of pi equal to 1. And I obtain my a to be square root of beta m over 2 pi. So now if I go back here, instead of a, I will put square root of beta m 2 pi, and I will get f of vz equal square root bm over 2 pi e to the minus beta half m vz squared. So we proved what the question is asking me to prove. Now, use the obtained function in order to find the expectation value of vz square, and we need to show that it is 1 over beta m, or kbt over m. And there is another hint that we will use for the integral. So what is the expectation value of vz square? It's the integral from minus infinity to infinity of vz square multiplied by the distribution function, which is fvz dvz. And this is equal to, now instead of fvz, I'm going to put this thing that I obtained in the first part. So it is bm to the half over bm over beta m over 2 pi to the half e to the minus beta half and vz squared dvz. I'm going to take this constant value, which is square root of beta m over 2 pi outside, and I will have the integral from minus infinity to infinity of vz squared e to the minus beta half and vz squared dvz. Again, I'll do the same trick. I'll say let x squared be equal to beta half mvz squared, and then vz will be the square root of 2 over beta mx. So dvz will be the square root of 2 over beta m dx, implies the expectation value of vz squared will be equal to this term over here, which is square root of beta m over 2 pi, the integral of, what do I have? I have vz squared, which is this term square. Okay, so it is 2 over beta mx squared multiplied by e to the minus x squared multiplied by dvz, which is square root of 2 beta over m dx. Okay, and what will this give me? This will give me, I'll just do some math here. I have beta m here and beta m here. I'll have square root of beta m, and then I have a beta m here. So this will give me 2 over beta m, and the 2 to the half. So just do the simple math, the 2 will remain, and I will get, and I will use the thing that integral from minus infinity to infinity of x squared e to the minus x squared is equal to square root pi over 2. So I will get the expectation value of vz squared is nothing but 1 over beta m, and this is equal kbt over m. Uh, Here there is just one thing. This beta is not here. So this is dvz. It is square root of 2 over beta m. So the beta is down here, okay, in the square root. And that's why this bm and this beta m, they cancel out, and I will have only 2 over beta m left. And this square root 2, this square root 2 will cancel out, and I will have 1 over square root 5 remaining, okay? And this is how I get the expectation value for Vz squared. Now, deduce the average kinetic energy. The average kinetic energy is nothing but the expectation value of kinetic energy is nothing but half mvz squared. Half m will go outside, and this is the expectation value of Vz squared, which is kbt over m. So it is half m kbt over m, and this is half kbt. Okay, so now we need to show that the kinetic energy in a 3 dimensions is a 3 over 2 kbt. So expectation value of kinetic energy is half mv squared. In 3 dimensions, it will be vx squared plus vy squared plus vz squared, which is nothing but half kbt plus half kbt plus half kbt, and this will be 3 over 2 kbt. And from that, if I'm to deduce the heat capacity, remember that the heat capacity is nothing but del expectation value of E. Sorry, before that, so we need to show that the expectation value of energy, this is just the kinetic energy. Now we need to get the expectation value of the energy, which is the kinetic energy plus potential energy, but the expectation value of are equal. So we will get the expectation value of energy is equal to 2 expectation value of Ke, which is 3 kBT. Now, what is the heat capacity? The heat capacity is nothing but del E by del T, and that's 3 kB. And this is exactly what we found for the law of DeLong and Petit, okay, that the heat capacity is 3 kB. Okay. Now, the second problem. So now we will start with classical Einstein or Boltzmann solid. So consider a 3-dimensional simple harmonic oscillator with mass m and spin constant k. Calculate the classical partition function given by z equal 1 over 2 pi h bar cube integral of this thing. Okay, so this is just the classical distribution function in 3 dimensions, where the Hamiltonian is h and the q is the canonical position and p is the canonical momentum. And here again, they are giving me some hint that I'll use. And then we're gonna use this partition function to calculate the heat capacity. So we will calculate Z, and then remember that E is nothing but del ln Z by del beta. And then from E, we're gonna calculate C, which is del E by del T, okay? And then we're gonna solve the same problem using quantum Einstein model that we are going to introduce this quantum partition function. So instead of taking it to be the integral over all values, we're going to take it only based on the energy eigenstates. Okay, and remember, En is nothing but n plus half h bar omega. Again, we're going to find an expression for the heat capacity. We're going to find the high temperature limit, and we will show that it agrees with the law of DeLong and Petit. So it will agree with part 1 here, with part A. And then we have to sketch it. In order to sketch it, we're going to also find the heat capacity at low temperatures, and we will just interpolate the figure, the values. So let's start. So we have this Z value, and we want to calculate. So let's calculate this Z first. So the Z is 1 over 2 pi h bar cube integral of d cube q d cube p e to the minus beta h. I'm just starting with the definition. What's the Hamiltonian? The Hamiltonian is the kinetic energy plus the potential energy, and this is p squared over 2m plus half kr squared, which is px squared over 2m plus py squared over 2m plus pz squared over 2m plus half kx squared plus half ky squared plus half kz squared. So z is 1 over 2 pi h bar cube, the integral of dpx, dpy, dpz e to the minus beta over 2m p px squared plus py squared plus pz squared. So I divided it into two integrals, one having dpx, dpy, dpz, and one having dx, dy, dz. This is okay because actually if I don't make two, they are just the integral from minus infinity to infinity of all these multiplied by each other. But I divided it by two. Okay, so this is equal to this thing is just a constant, it goes outside, and this is the same thing cube, so it is the integral from minus infinity to infinity of dpx e to the minus beta over 2 and px square cube, and the second thing is in the second, and this form, this value is also the integral from minus infinity to infinity, dx e to the minus beta over 2 kx squared. But here I'm going to use the fact that the integral of from minus infinity to infinity of e to the minus au squared du is equal to square root pi over a. So from here, the a for the first term, the a is beta over 2m. Okay. So what will I get for the integral from minus infinity to infinity of dpx e to the minus beta 2m px squared? It will be square root of pi over a, which is over beta over 2m, where a is this. And for the second term, I'll get something similar. So this means z is equal 1 over 2 pi h bar cube square root of pi over beta over 2m cube square root of pi over beta k over beta k over 2, but omega squared equal k over m. So here I'm using the fact that omega squared is equal to k over m. So k is equal m omega squared. And then if I just plug it in this formula, I will get z is equal 1 over beta cube omega cube h bar cube. Okay. So I calculated the z. Now, using the partition function, calculate the heat capacity. So the expectation of E is nothing but minus del n z by del beta. But what is len z? It is len 1 over beta cube omega cube h bar cube, which is minus 3 len beta h bar omega. And the expectation value of E is minus del len by del beta. So I put here the len of Z, and I get 3 over beta, which is a 3 kBT. Now the heat capacity is del E by del T, which is a 3 kB, and this is indeed in agreement with the law of DeLong and Petit. Okay, so if we use the classical partition function, we get C equal to 3 kB, which is in agreement with DeLong and Petit. Now let's do the same thing, but using quantum mechanics. So again, instead of taking the integral, when we talk about quantum mechanics, we take the Z to be the summation over all eigenstates. And what is En? It's equal to h bar omega into n plus half. So Z is summation of e to the minus beta En. And you can just go back to lecture 15. I've done exactly what is done here. So we find that Z is e to the minus beta h bar omega over 2 divided by 1 minus e to the minus beta h bar omega. In 3 dimensions, this is nothing but this thing cube. So just go back to the lecture, it's shown. So we get that Z in 3 dimensions is e to the minus beta h bar omega over 2 divided by 1 minus e to the minus beta h bar omega, all of it cube. So we calculated the partition function. From the partition function, we calculate the expectation value of E, which is del n z by del beta. And you just follow the math here. It will give the expectation value of E is equal to 3 h bar omega of this thing. Okay, but we take this 1 over e to the beta h bar omega minus 1 to be nb of beta h bar omega. And we find, when we find this expectation value of E, we do the del E by del T, that is the derivative of E by del T, and this will give me del E by del beta by del T, which will result in the final value, just do the math here. This will give C equal 3 beta h bar omega square kb multiplied by del beta by del t, which is e to the beta h bar omega. I mean, del E by del beta will be 3 beta h bar omega square kb e to the beta h bar omega e to the beta h bar minus 1 multiplied by del beta by del t, which is nothing but kb because beta is equal to kbt. So we found this C. It is not 3 kb as we got for the law of the long and the t. It is actually 3 beta h bar omega square kb times e to the beta h bar omega divided by e to the beta h bar omega minus 1 square kb. So this is different. This is different from the long t, which is just c equal 3 kb. Okay, now we need to get the high temperature limit. So the high temperature limit, so this is my equation, okay? The high temperature limit means what? So if temperature, high temperature, so if temperature is high, implies beta is kBt, right? So beta is kBt. So beta is high. T is high. Implies beta is high. So in this case, I will come here and I will have just a second. So here. So if temperature is high, implies beta is low because beta is 1 over kBt. Okay, so it is the inverse of the temperature. So if T is high, then beta is low. So I will have in this term, e to the beta h bar omega will be much less than 1. Okay, so it's very small. So beta h bar omega is much less than 1. Now, what is e to the x? It is 1 plus x over 1 bar plus x square over 2 factorial, sorry, plus etc. So e to the beta h bar omega, it is very small, so we will take it's almost 1. And e to the beta h bar, so we will take the first term for e to the beta h bar omega. For e to the beta h bar omega minus 1, we will say it is 1 plus e beta h bar omega minus 1. I took 2 terms here, the first and the second term, so as I don't have 0 denominator. And then the c, if I just plug this thing in the c equation, which is here, so it is a 3 beta h bar omega square kb multiplied by 1 over beta h bar omega square. The beta h bar omega square cancel out with beta h bar omega square, and I will get c goes to 3 kb, which is indeed in agreement with the law of Dulong to T. So this happens at high temperature. At low temperature, beta is very high. At low temperature, beta is very high. So if I go to the equation C, I cannot cancel out. So here, this is a 3 kb beta h bar omega square e to the beta h bar omega divided by e to the beta h bar omega minus 1 square. And this is a 3 kb beta h bar omega square e to the beta h bar omega divided by e to the 2 beta h bar omega, because here I just did, I did it e to the 2 beta h bar omega plus 1 minus 2 e to the beta h bar omega, but this is very high, so what will remain is e to the 2 beta h bar omega, and I will get that this will go to 0. So at the very low limit, it goes to 0. At the very high limit, it is a constant, and this is how it will look like. So the last part is to sketch the heat capacity. I calculated it at low temperature, and I sketched it. Okay, so in today's lecture, we reviewed the law of the long entity. We reviewed Einstein introduction, what he introduced in order to solve for the problem, and we solved exercises based on that. Actually, all the derivations that were done for Einstein quantized model, it is also done in lecture 15. So if here I went a bit too fast, you can go back to lecture 15 where I've done things more slowly. In next lecture, we are going to introduce a new model, which is the Debye model, that actually solved the problem at very low temperatures. Okay, so that's it for today. Bye-bye.